filled. It's been filled by Martin Poole, who currently works at Google, and prior to that spent several years working at Canonical, and he's talking about a little process tool that he is working on and has developed. The title of his talk is Remedies for Frustration with Speed, Quality and Reviews. Please everyone give Martin a very warm welcome.
Well, hi, thanks very much. Yeah, this isn't so much a talk about a particular software tool as about some ideas that I've run into over the last few years or come up with that I think are very useful for the future. I hope you might find them useful too. I've written a fair bit of software over the years, and I made a lot of mistakes. I'm not ashamed to admit it. Some things I've done have worked out well, and some of them have not. I'm not going to do a post-mortem or a history of Bazaar or any other project today, but yeah, some things to keep in mind. This quote. You can justify just about anything if you put Einstein's name next to it, and many people have tried. Oh my god. So, yeah, let's start with performance. The program being fast enough to feel like it's working with you and not kind of getting in your way or slowing you down. Bazaar was way too slow in its first releases. It started out as an update to GNU Arch, or a rewrite of GNU Arch, and it was faster than that, but it wasn't fast enough in absolute terms. And eventually it got a lot faster. But in the meantime, it really frustrated and disappointed people and lost a lot of users in the early days. And I think one thing that caused that was that in the early releases, we thought a lot about the UI behavior and the user model we wanted to have, and we took an intentional strategy of making it work, making it correct, making it fast, especially when we were starting from a system that worked but had a really unlikable UI. And the UI was okay, but one thing I learned from that is that this thing of avoiding premature optimization is a really dangerous concept. It seems to imply you can defer all consideration of performance until you have the UI you want, but it turns out that if you bake into the UI or the API or the data formats some things that are going to be hard to implement quickly, it's really hard to unwind that. It's line from one of our developers, Yama. So now I have a more nuanced view of that, and I'd rewrite it to say something like avoid premature micro-optimization and ask yourself how expensive will it be to come back and change to a faster implementation later on. If it's one function or one routine that's fairly self-contained and you have a straightforward, maybe slow implementation, you can rewrite it. It won't cost you anything extra. But one specific example we had was that the user model showing the number on a revision tended to require traversing the whole graph of revisions up to that point. So it's inherently order n or worse in the whole history of time. And changing that would either require changing the user interface or changing the formats or adding a cache, all of them a bit hard. Or another thing where not considering performance can bog you down later on would be internal APIs or structures. So, for instance, in Launchpad, a lot of the APIs internally and also across the network were one object at a time. There's a URL for an object, you can get it or write it back. Which sounds very straightforward, but it's really painfully slow if you want to search through hundreds or thousands of bugs to look for something or do a bulk update on them all. John O'Lang, I think, coined the term for this potato programming. It's one potato, two potato. If there's a network round trip, very annoying. And also data formats. Original formats were a bit naive about performance. But getting everybody to convert to a new format to be faster, also kind of annoying. So what I would say now is that add in a requirement right from the start about what performance goals you have to eventually hit. So for instance, something like a tree of 10,000 files with 100,000 revisions, and you have to be able to at least detect nothing changed within a second. Your very first version of the code might not do that, but you can make sure that you're not doing anything which is going to make that impossible or hard to do later on. And you can do this kind of thing for other qualities like robustness. If you're designing a storage system, you might say right up front, we need to be able to lose any single disk or any single server and still get back all of the data, and then never lock in any decision that's going to cause trouble with that. Another piece of advice from a very famous Google programmer, Jeff Dean, is to do all of this planning on the input being about 10 to 100 times what you think it will be. So if you're planning on dealing with 1 gigabyte files, do your architecture work assuming files are actually going to be 10 gigabytes or 100 gigabytes, which would imply you can't really count on holding them all in memory. You have to, take some approach which doesn't count on that. And then, first of all, that gives you a bit of margin for error when you implement it, that if it turns out to be a bit hard, you have some slack. And then also, inputs do tend to grow over time, and that will give you a bit of longevity in the core designs. So one more concrete thing we did for this. Tridge said once actually that untested code is broken code, and I think that's also true for qualitative things like performance. If you don't test performance repeatedly, it will break, it will get worse. Now, there's no substitute for testing real-world performance, like get the tool on your thing, get a large input data, run it, measure how long it takes. I wrote a little utility judge where you can give it 2 programs and the same input parameters, and it will do, not just run them and print the time, but do kind of statistical tests as to whether there's really any difference or whether it's just noise. And many continuous integration things will help you track this too. But the problem is real-world measurements of performance always have a lot of noise in them. There's contention against other tasks on the same machine. There's, paging, or the file system is a little bit faster or a little bit slower on different things. And if you're trying to take care of network speed, that's even worse. There's even more factors that are very hard to control. And if a human's looking at a graph of performance over time, they can see it's going along, it went up, it went down, that's okay. But really, we'd like to have a machine do this so that a machine can look at branches which are proposed to merge and say, no, that's not going to merge because it breaks the test suite, or because it would make things slow. You keep the tree always green with regard to performance as well as function. And one solution we came up to with this is what I call deterministic effort tests. And the idea there basically is you identify an operation that correlates with performance, but that's also deterministic for any particular run of the program. So, for instance, the time it takes to do a network request might vary quite a lot depending on network conditions, but the number of requests that you have to do a user operation might be predictable. And if somebody changes the code so that it does more requests to achieve a particular result, then you can flag that that's going to be a potential problem, and you can decide it's acceptable or not. And we did this. It worked very well. Not only does it keep your tree green, it's actually faster for the developers because they don't need to make a judgment call about whether this thing is 3% slower. Is that actually significant or not? They just get right away an answer. One subtlety to this is that you might think, okay, so I'm going to add an assertion that this takes less than 10 network requests to do its thing. That's not bad, but sometimes it's actually better to say this takes exactly 9 requests if it really is deterministic. Because then if somebody fixes it, so it now only takes 8, then the test will fail, and then they update the test to say now it takes 8, and then if it regresses, it will fail again, and you can pull that up. Although it's complicated, it's a judgment call. Another thing like this is memory use, which also very important to behaving reasonably on large inputs on arbitrary machines, and also very noisy, so a bit hard to deterministically test, especially in scripting languages or GC languages. Though I have talked to a friend who's a game developer who said, you can't swap on an Xbox or something like that, so every dynamic allocation basically has to be justified in the code. But you can't do that in Python. So one thing we did was put in a budget, basically say this operation is allowed to use memory equivalent to 1 times the input file, but not 2 times, or you say it's got to be constant memory size, even however big the input is. And then just simply set a U-limit on the program, which is kernel control says how much this process is allowed to allocate, run it on a large input, and it will either crash or not. And if it crashes, it's statistically very likely to have stopped at the point at the call stack that's doing most of the allocation, and that's the bug right there. And just quickly, a couple more specific things. One thing, this thing, tcqdisk, TC is a command, fairly horrible user interface, but it lets you get at the kernel's internal traffic control stuff. And this, you can say traffic to localhost on this port, delay every packet by 300 milliseconds, or drop, 0.5% of packets or something like that. And right there, your app running there will behave a lot like it's running in London and you're running locally, except more predictably. And you can run an automatic test, or you can just play with it and see if it feels acceptable at that level. The other one here, drop caches, it's a bit self-explanatory. Discard all the VM caches, so any I/O will do a hard I/O to disk, and you get more predictable behavior from one run to the next. Another kind of specific performance thing that we learned about, we were really trying at first to have a pure Python implementation, so to be easy for people to hack on it, easy to run it everywhere. I think that was a big mistake, basically. The key thing, of course, is, like I talked about earlier, to get the right algorithms, the right data structures, that it's possible to get the right big O behavior. But even if you have the right big O, you still want low scaling factors. And it turns out some things in Python are really expensive. A function call is quite expensive, on the order of a microsecond. Creating an object, also quite expensive. So you can optimize Python by not doing too many function calls, inlining code, using tuples rather than objects. They're, I think, 20 times faster. But you end up with something which is pretty gross. It has lots of indexing to objects using integers, lots of deeply nested code in one big function. And at this point, you're not getting much benefit out of using Python. What we really should have done there is get the algorithms and the formats right, write a straightforward thing in Python, and then if it's hot, drop it right into C or into Cython or Pyrex, which are kind of compiled versions of Python that work very well. So if something is slow, and it's a bit hard for whatever reason to inherently change the slow code, like maybe you've set requirements around that thing that it do a slow operation, obvious solution is to put a cache on it. Not always a bad solution, but also kind of a dangerous path. Caches can improve the average response time that you see for things, but they don't improve the worst case response time. When the cache misses, and they may hurt it. And you may end up with a program that is often fast and sometimes really slow, but user experience or users' kind of subjective impression of the program is often shaped by the times when it fails, not the times when it's acceptably fast. And so if the worst case is still too bad, You may not have totally solved the problem. You may have made things a lot more complicated. You have to consider the state of the cache when you're debugging things or when you're profiling things. You need to consider when the data changes, will the cache be flushed, always correctly flushed, or can you quickly validate it? And in Launchpad, we had some really, in retrospect, interesting failures where caches were now overflowing, and something that was doing quite okay is now thrashing totally. Yeah, so a few thoughts on performance. I'd like to go on to now to quality and think about how we can get quality in releases and what quality really means. And as a bit of a bridge, we want to write tests. Some of these tests are to things that are external or unreliable, unpredictable. Maybe it's a network, maybe it's something that's slow to set up locally. And many of you will have encountered the idea of using what are various called mocks or fake objects that simulate some other resource, but in a cheaper or a more easily testable implementation. What I see in a lot of code now is that the mock libraries, like mocks in Python and so on, encourage you to define the mock inline in the test. But if you do that, the mock can drift from reality of how the thing really behaves. The test is still working the way the test works, but it's not representative of how the real thing would work. What I would do here in future, what we did in Bazaar for a long time, what I would continue doing in future is to put the fake object next to the class that it fakes out and have that be one unit of maintenance. So if there's a network server class or a network client, then in a file right next door, provide a fake one. Don't do it inline in the test that use it. Say, as part of the contract of this expensive resource, I also give you a cheap but not durable or whatever version of the same thing. And then there's a very nice Python library started out in Bazaar, factored out by Robert, called test scenarios, where you can basically express that a certain test suite needs to have the same behavior across two different objects, and in that way say that make sure that the fakes don't drift from reality, because you do actually exercise them with exactly the same test code as the real thing. Now, zooming out again to something a bit less technical, a bit more abstract, this concept from lean systems thinking of done. Like, what is really done? Is a feature done when you commit the fix for it? That's the obvious thing to say, perhaps. But I suggest to you that's not really true. It's not really done. Lean people would have us say that it's done when the work is available to all the users and the users are happy that it's happy with the result. And if you lose sight of this distinction, it can be easy to lose track of things once they're committed to trunk and think, well, kind of wash your hands of it. But it's not. Sorry. Sorry.
It's done when the last user passes.
Yeah, maybe. I mean, the program as a whole maybe is done when nobody is using it, but a particular feature is done when people are happy with it. Yeah, and it's the user who judges, ultimately, that the thing is adequately done. I'd like you to think about the event cone of a change that you make, and how many people experience that change over time, and how they test it. When you first make a change in your local client or whatever, you test it yourself. It's exposed to one person, and then you put it up for a review maybe, and more people test it, and then it goes through beta testers out to the whole world. So it expands over time. And there will be, as you do work, there will be bugs. There's value in catching the bugs sooner rather than later. But there are some bugs that require a lot of exposure to catch them. Maybe they only occur in kind of unusual environments. Maybe they only occur when you use the product in a particular way. Maybe maybe they're just a thing where you need a fresh pair of eyes to notice that it's a bug at all. If you think about this cone, you can think about the shape of the cone, right? And think about, as we progress from one step to another, what is the risk that we're passing on bugs that would be avoidable to a larger audience of users? And also, what is the risk that by staying in this state, we're not actually catching any more bugs, we're just introducing delay? It's easy for processes, like looking at the Ubuntu stable updates thing or various other things, it's easy for processes to accumulate testing time or soak time where in theory things are being tested, but in practice they're just kind of sitting there aging, and the rate of new bugs being discovered during that phase is declining pretty rapidly. So if you try to make them shorter, then you can think of alternative approaches to releasing. Maybe you can release faster but make it cheap to roll back. Maybe you can say, actually, we're going to get to the bulk population of users quite fast, and maybe with a few more bugs, but we'll have a way for people to opt into a more stable one that gets, features later and gets fewer bugs. Now, sticking with this thing that we've done the work, but it's not really done until all of our users have it and are happy with it. Doing the work has a cost, but it doesn't have a benefit until it's delivered and accepted by users. And I want to suggest to you we should always be thinking about how to make that interval as short as reasonably possible. This is often, maybe it's obvious to all of you, but it's often a little hard for people to accept. It's easy to think, well, okay, there's quite a long pipeline, but we're ramming stuff into the pipeline all the time. They eventually pop out the end. There's not necessarily any problem here. Martin, why are you talking about latency when we should be thinking about the throughput of features? It's a good, it's a reasonable question, but there's a few answers. One argument is the concept of time value of money. You get benefits of some kind, presumably from shipping better software or shipping software at all. You get users, contributors, actual money. The sooner you get your work out to them, the faster those benefits can come in and the faster they can compound. If you imagine doing 0 releases for 5 years and then you release everything, the throughput was there, but nobody used your software, nobody gave you feedback. Maybe nobody wants it by the time you release it, whereas if you had released the improvement earlier, it'd be there. And of course, also unfinished code can rot. It can turn out that you're actually solving the wrong problem, or your code doesn't actually work, or whatever. The sooner you get that feedback loop, the better. So if we want to shorten this, what kind of thing introduces latency? I think you should look for cases like these. There are probably a lot more of them than you think. And kind of systematically observe them and try and squash them down. I make a commit. How long does it take for it to get reviewed? How long after it's reviewed does it take to get merged? How long does it sit on trunk for before we get a release? That's often weeks, months, maybe more. Okay, we have a release tarball up. Now, how long before there are binaries for whatever, assuming people install from binaries, how long until that exists? Okay, there are binaries somewhere. How long until they get into the update channel that all your users, the bulk of your users will get them from? If you're going through Ubuntu update channel, that's a pretty good thing. People can get lots of bug fixes pretty fast, but it's also very easy for there to be weeks or months of delay before users are getting your thing. And not just update in one channel, but update on every system that you've decided you're going to support. And for some things, just having the code out there is not enough, right? People have to discover that the thing is fixed or that the thing exists and they can use it, and then most of all, actually working properly, which might require restarting the whole process. So, what can you do? You can change your mindset from not giving yourself credit or giving your teammates credit for work. I mean, I don't mean be mean, but have a sense of impatience and a sense of incompletion until it's actually pushed all the way through to the end. Many of these are not automated, right? And that's why they stall, because you're waiting for somebody else to do it and it's not your job to do it, and they don't care as much about that feature, or it's not the most pressing thing. Handoffs. It's really good to avoid starting new work if there's anything you can do to finish off stuff that you've already paid the cost for or paid part of the cost. People tend to parallelize so that, okay, this thing is stalled, but I'm going to start something else, but this is a sign that something is wrong and that you might be able to just shorten the pipeline. Now, a related thing is that if you can make the pipeline short and get fairly quickly from doing some work to having it out there, then you can cut out another category of waste, which is trying to predict when something will be in. If you release only every 6 months or infrequently, you tend to get quite uptight about what will be in this release versus another release, or should we shift the releases around. And I think doing estimation work is a kind of undesirable thing for two reasons. One is it's quite time-consuming and consuming of energy. People could put into directly doing things. The other problem is that it's impossible. So you should probably avoid it. I say impossible because there's a ton of literature that for new creative work, people are very imprecise in estimating. They big error bars, and they're also very inaccurate. The error bars are all in the side of optimism, especially if you consider how long will it take to get to done. Moving on to another aspect of releasing. Some people would say we ought to track every bug we know about. They're all important data. I'm very skeptical about that now. I think the point of a bug tracker is to help the developers decide what they're meant to do next, what is their next priority, and to give them the information they need to do that work. And then to users, a bug tracker also has a function which is telling them, this is already known, there is a workaround, this kind of thing. Documentation. There is a very strong Pareto effect with bugs, which is that most of the users will hit a fairly small set of bugs, right? A 80-20 effect. The very good book, Getting Things Done, and it makes a very algorithmic observation about the way people organize the stuff they have to get done. That is basically, you should try not to make the same decision about the same data twice. If you keep lots of stuff in your inbox and you read it over and over and again, picking out one thing at a time to do, that's order n squared. It's not very efficient. So for bugs, we want to avoid spending time making the same assessment of the same bugs. There are really only 3 priorities for bugs. You're going to do it right now, like you're going to drop what you are doing and immediately fix this critical thing. You're going to do it soon, like in the next month or 2, or you're probably never going to do it realistically. You might think, well, no, that's too pessimistic. We'll do these critical things and the P1 things, and then we'll get to those. But there's a dynamic equilibrium here. The things that currently gave you the critical and high priority bugs, those processes still exist. Those, unless something drastic has changed, those queues will fill up again before you ever get to the low priority bugs. So you can measure this. You can see which things, how far down the list do you ever actually get. And I suggest you should just ignore the never bugs. You're not going to fix them. Any work spent on them is just waste. You should be pretty brutal about triaging them. Now, there are exceptions. There are some things where it doesn't seem very important, but 1 million people hit it, and so it gets upgraded, etc. But the default should be that anything on them is waste. Thanks. I don't think even trying to find out how many never bugs there are useful. For any non-trivial program, you can keep looking and you'll keep finding bugs as long as you like. You might as well assume there's an infinite set of bugs that you could fix if you got around to them. The more important question is how many developers times however many they do in a week times 4 to 8 weeks. That's the focus, the things that are worth spending much time investigating. Now, another important exception is that there might be some person in the world for whom this bug is actually really important, and maybe they can argue, I don't know, but maybe they're actually going to send you a patch. That's great. I'm going to talk about that later on. I think also people disagree about this. Some people think users feel better if they get an answer from the developer saying, thanks for your bug, that really sucks, priority low. I don't know. If they say that and they don't fix the bug, is it that much better than if they just don't fix the bug? Or if a robot says that and they don't fix the bug? Maybe it is. It seems.
I think it is actually. Speaking as somebody who has.
Okay, so let's do it afterwards. But it's arguable. But I think at least you should be very quick in doing those things. And another thing about how can we deal with lots of bugs. So Ubuntu has. Or Launchpad, all of the projects on Launchpad together have 1 million something bugs. Google bugs look like phone numbers. We want to deal with them really efficiently, the bugs that we're not going to fix. I think bug trackers work really well with discrete bugs, like when I type foo, it crashes, or when I type 2 + 2, it prints 5. They're really good because you can look at them and you can say that, I tested this and that bug is now fixed or not fixed, or at least by the time you get far enough into triage, those two bugs are or aren't dupes of each other. Bug trackers have a lot more trouble with feature requests or UI shortcomings or performance bugs. I don't totally know the answer here, except that I know you want to be careful not to have developer time sucked into gardening bugs that won't get fixed. If there's a bug that, commit is too slow, when is that bug fixed? Like, how fast is fast enough? Is that the same bug as, some other thing? We experimented with putting semi-arbitrary goals on the bug, like, commit should take less than blah, blah, blah on this situation. I'm not sure. That's how we can test and release. The part of this I care most about is community, and in particular, scaling your project by making it easy for new people to contribute to it. Think about how developers come to an open source project. Some of them, they want to get a job in OpenStack, so they send patches to OpenStack. But it's also very common that they have an itch that they want to scratch. Before somebody becomes a core developer, they have to send a first patch and a second patch. And I want to also apply kind of systems thinking to what happens when they send a first patch. Will they progress to sending a second patch, a third patch? Will they drop out of that process at some point? There's a kind of funnel here. Lots of people experience a bug. Some people think about fixing that bug. Some people actually fix it locally, get the patch up. We're losing more and more people at each stage who don't ever get their first patch merged, don't send a second batch, etc. Now, that funnel is always going to exist. We're not, it's just not possible that everyone will become a core contributor for every project. But I think you can improve the odds, and I think also this is some of the most valuable work that you can do because you're improving your own scalability in the long term. You don't have to write everything yourself because you're bringing in new resources, new people. So, you're very imaginative people. Imagine we wanted to make sure that somebody did not come back with a second patch. We hate this person's name. We never want to see mail from them again. What would we do? Well, one thing very easy to start with, just don't reply for a long time, right? That's pretty, that will discourage a lot of people. Then, when you do reply, just be really nitpicky. I think this is a widely held opinion. And then once they've fixed all the nits and they're almost there, ask them for a few more things. And then a couple of weeks later, a few more things. This is intermittent reinforcement. It works great. And then ask them to do something that seems really tangentially related to the bug that they actually care about, which got them into this thing in the first place. And then after that, have somebody else come along and ask them to do something different and, if possible, contradictory. You will probably succeed. So, yeah, I am a believer in code review, but we should be clear about what the purpose is. What do we really want from our project? Many of the things that tend to come up during reviews, like the details of how the code is formatted, are not necessarily the things that we would say we care most about in our project. Do you want to look back a couple of years from now and say that your project had, PEP8 compliant formatting all the way through? I suggest no. We want to make something our users love that brings us to work with really fun people and it is good to work on. If we really focused on these things, what would we do? People also, maybe more reasonably than this, people sometimes think code review is to catch bugs. And you can catch bugs in review, but I'm not saying you shouldn't pick up obvious bugs or you shouldn't read carefully for some code, but it's not the only way to do it. It's not always the most efficient way to find those bugs. I'm going to move through this a little bit. The key observation I want to make here is that the kind of patches that new developers send you are a different kind of patch to what established developers send you. Experienced developers, by definition, are doing the largest work and they're the most prolific. They're moving big hunks around, they're defining new interfaces, they're maybe changing the more hairy code. Their patches need a different kind of review. New developers are not going to be making big architectural changes, they're not going to be making very many changes. When we review their first patch, we need to bear in mind that it's their first patch and think about what that means. So we want no obvious bugs. We want probably some test coverage, and we want it written in basically the right way, but it doesn't have to be strictly minimal or the most elegant way. And we want to think about how can we conclude this thing that the person will be happy with the experience, they enjoyed sending us a patch, and they progress to be in a good place to do another patch later on if they want to. So prompt, helpful reviews. They will almost always have interactively tested their patch themselves to see it does basically the right thing before they send it to you. Writing good unit tests, although they are a very good thing, they can also be harder than writing the patch in the first place. So that is a place where people can really bog down. It may be that even if you expect your core developers to write really good unit tests, for new developers, it's okay to just say, here's an integration test that shows it works the right way, even if it's a little inefficient. Now, in Bazaar we did, one of the things I think worked out really well was patch piloting. We promised that if somebody sent us a patch that was basically along the right lines, we would help them land it, even if they didn't want to do the refactoring work or couldn't do the refactoring work or couldn't work out how to write tests. We will get it landed. We will use developer time, core developer time to get it in. To make that work, you want to track how many you need some tooling to make sure patches are not lost. You need to make sure that this doesn't get swamped below other things that developers might want to do. We had a rota to make sure they got around to it. And I think it's good if it doesn't just happen, but you kind of celebrate that it's happening, that you give yourself a little bit of encouragement to the people who are putting in the work for what can at first feel unglamorous, and help other people see that it's a thing that exists. And yeah, if you go away and do things in your own project, these are the things that I hope you will think about doing in the future. I think they worked well for us, and I think they have a lot of value. So, questions? 1 minute of questions or something.
We have a little bit of time for questions. I'm looking for hands. If I don't see...